So a number of years ago, there was a nurse working in a hospital, I think in Massachusetts, and her fellow nurses noticed that, gee, while Gilbert was working, there's a lot more death that occurred than at other times. And so they started kind of looking at things, and they came up with this table of data here. And it shows the number of deaths when Gilbert was working and when she was not working, and then in other shifts. Now, if you look at these, you can form some proportions. And maybe let's do that. Let's take a look at, let's do 40 divided by 257. 40 divided by 257. So about 15.5% of the time while she was working, somebody died. Compared to when she was not working, we've got 34 divided by 1,384. Oops, 84. About. I'm adding these two, right? That way you get the total number here, which would be 1,384. And then up here was 257. So about 2% of the time. So, wow, that looks pretty bad, right? I mean, I wouldn't want to be a patient in the hospital while she was working. So, what's that? Yeah, this is. Well, that's a good question. Is this unfair? Because I mean, there's so many other, people here when she's not working. So maybe she's working at the popular shift. Who knows? But what we can do is we can do what's called a chi-square test for association. So this is on the back side of your handout. Chi-square test for association. And what this does is it helps us decide whether or not two variables are independent or are they associated. And that's all we can decide. So we can't say that the one necessarily causes the other, which is important distinction. In fact, let me take the opportunity to go back and review something. This is based on your comments that you gave me after my lecture last week, proving a cause and effect relationship. There was 5 things that I said that you needed to establish in order to prove a cause and effect relationship. 1 is the correct temporal order. 2 is replication of studies. You should have study after study showing similar or the same results. You should have, where possible, a dose response. You should have longitudinal studies. So longitudinal studies. And there was a different name for those. It's called cohort studies. But the thing about these is that they helped control confounding variables. And that's one thing you should know. Helps control confounding variables. These are other variables that might, interrupt the causal relationship between two variables. Let's see, temporal relationship, replication study, dose response. Oh, and last but not least, you should have a plausible causal mechanism. You should be able to explain the result. Now, this case is not a statistical study. It's not something that we can really apply this to. But it also makes clear that this kind of a study or this application of statistics isn't appropriate for establishing a cause and effect relationship. this is just a snapshot at a point in time. It's tough to decide, gee, does one cause the other? Certainly there's a temptation to, but you can't. You can't go beyond the fact that all we can prove here is an association. So, okay. Well, let's see how we're going to work with this kind of a data set. So going back to our chi-square test of association, it's very similar to our chi-square goodness of fit test in some ways. That is, we're going to calculate a test statistic here based on the difference between observed and expected values. Now, how we exactly calculate that is perhaps more than we need to know. It's based on some ideas of probability that really aren't beyond the grasp of this class, but pretty much everything that you can run into in terms of your graphing calculator or statistical packages are going to do this for you. Suffice it to say that they're going to calculate an expected value, much like you did for the mean of a binomial random variable, which was n times p. That's how we calculated things. So they're doing something similar to that to calculate the expected values, summing them up, squaring them, etc. All right. So let's plug this into StatDisk, and you're going to plug in the columns of data, and then we're going to go pick a different test this time. So let's see here. We'll close out these. I can clear out this data. And we just have a couple quick columns to work with. 40 and 34 for one column. And where's the other one? 217 and 1350. So pretty nice. While you're entering those, I'll close out a couple of other things here. Let's do this analysis at what level? If you're trying to decide, gee, should we look after this person for murder, what level do you want to do the test at? 5%? 1%? 1%? Okay, sure, 1%. All right, so we'll test a claim at the 1% level that there's no association between whether or not Kristen was working and whether or not a patient died. All right, so let's come back here. H sub 0, there is no association between whether Gilbert was working and a patient died. Now, the alternative hypothesis is that there is an association. That is, there's some relationship between there. But we can't say that it's a causal relationship. We can't say that, oh, she's guilty of murder based on just this table. All we can say is that there's an association. So there is an association between patient death and Gilbert working. That's it. Yes, sir. Yeah, you're right. This is a little bit different. Our null hypothesis is that there is no association, and it's based on the idea that the two variables are independent. The probability of death is independent of her working or not. All right, and in that case, it is a little bit closer to what you're saying. It's just kind of tough to see it based on the wording here. But it has to be set up this way. That does kind of reflect the spirit of what we've been doing all along. That is, the null hypothesis contains a probability of equality or possibility of equality. Now, in concluding this, like I said, the most that we can conclude is that there's an association. You could not convict her in a court of law based on this table alone. In a court of law, you could say is that, hey, there's an association. The defense lawyer would say, well, you know, it's not a crime that she smells bad and she smells so bad that it killed him. I mean, that's the most that a lawyer in a court of law could do with this table. You cannot prove causation. All right, let's go through with the analysis part of it then. We're going to do this analysis at the 1% level because it's important to us to get it right. So back to Statistic, down to analysis. This time we want a contingency table. What columns are our data in? Well, we've only got columns 1 and 2. So let's select those. It's going to prepare for you a chi-square test. I haven't decided in my mind yet whether or not I want you to be able to do this for yourself or not. But the degrees of freedom for your chi-square test come from this calculation. R minus 1 times C minus 1, where R is the number of rows in your data set, and C is the number of columns. So in our case, there was 2 rows, so 2 minus 1, and 2 columns. So 2 minus 1 and 2 minus 1, 1 times 1 is 1. So you have a degree of 1 degree of freedom for your chi-square test. Before we do our chi-square test, one other thing I should mention is that in your table, each cell has an expected value of at least 5. So you should expect at least 5 in each one of these cells. There's a similar requirement for the chi-square test, chi-square goodness of fit test. And I think I forgot to mention that for the last section, but in each of these chi-square goodness of fit tests and tests for association, the expected values have to be at least 5. So that's why when we made up our data for Benford's test, that I chose, or I had you guys create 7 of your own cities so that we had an expected value of at least 5 in each of those things. That expected value is just n times p. Okay, let's finally finish this one up then. If you click the 2 columns that we have, you know what? All right, let's do that. Let's change it to 1%. It's not going to change our p-value. It is going to change the critical value. All right, and let's take a quick plot at that. What's happening is that your chi-square test says, all right, well, with 1 degree of freedom, we expect that point with 5% of the area in the chi-squared to be in the right tail is right here, 6.6, or not, actually not 5%, 1%, 6.635. Now the observed value for our test statistic was 86. So it's way out here. I mean, it's just unbelievably far here. So one of 2 things is happening. Either we observed a very unlikely event, or the null hypothesis is false. What do you think? reject H naught or fail to reject H naught? Reject H naught. Yes, reject H naught. So our decision, so step 5 is reject H naught. So our conclusion is that there is an association between whether or not Gilbert was working and a patient dying. There is an association between patient death and whether or not Gilbert was working. The follow-up on this was, I think that the evidence that we have here about patient death and whether or not she was working was enough to get a grand jury to look into this further, but what they eventually had to do to convict her was try and catch her. And I think they caught her stealing epinephrine, which is what caused heart attacks in all these people. So they did convict her, and she's in jail for the rest of her life. So they think that she was trying to be a hero and demonstrate what great skills she had by recognizing that, oh, somebody has cardiac arrest, and being the first one in there to help her recover. You know, it's pretty sick. It's tough to describe the motivations of somebody who would be a serial killer like this and do this just to make herself look good. I don't remember the story completely. I think she might have had a boyfriend involved too that she was trying to impress. But yeah, you can look it up. I think her name is Kristen Gilbert. But if you Google it, you should be able to find it. Yeah, Kristen Gilbert. There you go. So, yes, sir.
In the last problem, the p-value was 0.0000.
Yeah, p-value is.
That's the basis for rejection.
Absolutely, yeah. P-value was way smaller than any of our possible alphas. It's not something that we've done much in this class, but there's a lot of different ways to conduct hypothesis tests. You can conduct it based on a p-value, which I find to be tremendously convenient. I think you guys have done well working with the p-value. Or you can do it based on kind of a more traditional approach, which is to figure out, all right, at what point are you getting a result that's beyond the 5% or 1% significance level? So you find that point, and for the chi-square distribution here, it was 6.635, and then you look at where your test statistic falls. Our test statistic falls way beyond that. And the fact that it is way beyond that is reflected in the p-value, which was essentially 0 as far as StatDis is concerned. I think some other packages might actually show you the p-value. You know, they might give it to you in scientific notation rather than giving it to essentially 0. But yeah, it's very unlikely that you would get this result by chance. Okay. Any other questions on that one? Let's try another one or two from this section. Problem number 18. You know what? 18 looks like a long... No, I don't feel like typing all the data. I don't know, it's up to you. We're going to have to type in some data one way or another. We can work with problem 16 or 18. So let me give you a glance at both of those. 16 is working with injuries and motorcycle helmet color, or baseball player births. So, yeah, 16 looks a little bit easier in terms of at least typing in the data. So, a case control study was conducted to investigate a relationship between the colors of helmets worn by motorcycle drivers and whether they are injured or killed in a crash. Results are given in the table below based on data from motorcycle rider conspicuity and crash-related injury case control study. Test the claim that the injuries are independent of helmet color. Should motorcycle drivers choose helmets with a particular color? If so, which color appears to be the best? Okay, well, let's put in some data here. And yeah, we're still in section 11.3. So we'll go back to Statistic. Clear out the old data. Now when you're putting in data, you're going to be entering in rows and columns. So let's see, 491 wore black helmets and they were in the control group, and 213 were in the injured or killed group. 377 wore white helmets, and 112 were killed or injured. As far as orange helmets were concerned, orange doesn't seem to be a very popular color, does it? 31 and 8, respectively. Red helmets, 170, and 70 were in the killed or injured category. And last but not least, blue helmets, 55, and 26 were killed or injured. Our null hypothesis is that there's no association, or is that injuries and helmet color are independent. Injuries and helmet color are independent. What should I state for the alternative hypothesis? There's an association. There's an association between helmet color and injury/death. They didn't give us an alpha here, so what alpha do you want to use? All right, 0.05, that works. Step 3, we're not going to be doing this in the old school way, so step 3 is to enter the data, which we already did. So let's go to Statistic and run some analysis down to contingency tables. Before I do this, can anyone figure out how many degrees of freedom are going to be associated with this test? Degrees of freedom. Yeah. So there's 2 rows, 2 minus 1, and 5 columns. So 1 times 4 should be 4 degrees of freedom. All right, so I agree with that. Thanks, Chris. We're going to do our test for columns 1 through 1 through 5. So click those. We've got the significance level correct. Then click Evaluate. Ooh, nice and close. Ryan, what do you think? Reject or fail to reject? Yes. Just barely snuck in under the 5% level, but that's okay. So at the 5% level, we're going to reject. Let's see, Dan, at the 1% level, would we reject? Yeah, at the 1% level, would you reject or fail to reject? Yeah, fail to reject. So it's in between. It's nice to give the reader, this information, what the p-value was for your test, so that they can make their own decisions. It depends on the conclusion. It depends on the importance of the study, the consequences of a type 1 and type 2 error. But in this case, we're going to reject H naught, and let's state that in words. Let's see. So our conclusion is there is an association between helmet color and injury/death for people riding a motorcycle. Well, that's kind of strange. In looking at this initially, I wouldn't think that there should be any correlation or association. But there's a follow-up question. Before I get to the follow-up question, are you comfortable with what we've done so far? Doing all right there? Let's see. It says, what color appears to be the best? How would you decide if you're looking at this and you're going, oh, well, yeah, I guess there is an association. If there's an association, then they're not all the same. That what it's saying is that your chance of being injured is not independent of the color of your helmet. So what color would you pick, or how would you decide what to pick? Blue? How would you decide that? How did you decide that, gentlemen? Is it? Okay, I didn't grind those numbers. Oh, you calculated these probabilities already? So 704, 489, 39, 240, and 81. So let's actually calculate these ratios then. The percentages of people that are injured here. So 213. Let's see. 213 divided by 704. 30%. So 30.2%. And then 112 divided by 377. Nope, not 377, 489. 112 divided by 489 is 22.9%. 8 divided by 39 is 20.5%. 70 divided by 240 is 29%, 29.2%. And 26 divided by 81, 32%. Yellow orange, yeah. I'd be I'd be a little more comfortable with this conclusion if they had a little bit more data for people wearing yellow and orange helmets. I guess they're not that popular. Um, okay, so there's an association. Now, whether it's causation or not, I don't know. I think the best we can say is there's an association. Can't necessarily say. Yes, sir.
I guess this is more of a minor detail, but do you, would it probably change it if it was including like metallics in the paints?
It could. Yeah, if you further subdivided this by whether or not it had a sparkle to it, or if it was just a solid color, right, it might change it further. What that could give you is another set of rows. Actually, it'd be two more rows if you broke it out into metallic and non-metallic. Yeah, so you would just have a larger contingency table, but the analysis would proceed. Yeah, it'd be interesting to know that. Yeah, thank you. Okay. Any other questions on this one?
Summarize
16. Yeah, 16 for the motorcycle one. And I'm going to let you do this one. You can help each other out. That's fine. So oops. Okay, so what we found when we did the analysis is that there's, let's see, I guess we have to decide on alpha first. We can assume alpha is 5%. I don't think that the conclusions here are going to be that earth-shattering one way or another that we want to go to 1%, but then, that's up to you. If you enter all the data and run the calculation, I think you got a p-value of what, 0.71? 0.71. Do I need to enter the data for you guys, or are we okay with that part? You're good? 0.71. Now, with that p-value, are you going to reject or fail to reject? Fail to reject. Good. So there is not sufficient evidence to warrant rejection of the claim that the amount of cigarettes smoked and use of seatbelt are independent. Or you can just say that, you can say that in a variety of ways. And I came by each of you and looked at what you had. But basically, there's no association. These two variables are independent. Some wording to that effect should be your conclusion. Now, the author did ask some follow-up questions. And one of them was, a plausible theory is that people who smoke are less concerned about their health and safety and are therefore less inclined to wear seatbelts. Is this theory supported by the sample data? What do you think? Not really. No, because if that were the case, then we would see some kind of an association. You would see a significant proportion of those who smoked more and more not wearing seatbelts. So we're not seeing that enough from our data to reject our null hypothesis of no association. Okay, so for homework, try 1 through 21.